Welcome to the Creating Task Programs presentation, which is part of our series on learning how to use dexterity. The goal of this talk is to introduce some of the general concepts of custom task programming. There is an assumption that you already have some familiarity with the various tools that are used in custom task programming. So if you aren't familiar with MATLAB, Simulink, and Stateflow, I suggest you pause here and go and look at our user guide for some suggested readings and practice sessions that you can take in terms of familiarizing yourself and learning how to use MATLAB, Simulink, and Stateflow. The concepts that are presented here are also covered in our Creating Task Programs user guide. And there are lots of other details and examples beyond what we talk about here that can be found in our user guide and website. And as a point of reference, screenshots in this presentation are from MATLAB R 2019B and Dexterity 3.9. So if you're using a different version, then the screenshots might look a little bit different. It's good to start back at the beginning about how task protocols and task programs work with each other. And this slide is the same slide that you would have seen in the previous presentation on task protocols. But as a reminder, a task program implements a generic paradigm. It's really important that it's generic. Parameter values are not specified. So we don't specify things like where targets are or what the forces might be. We simply say that there will be a target and there will be a force. And the details about those targets and forces, so the actual values, are left for the task protocol. So these two things work together. Both of them are needed to run a task. I want to describe a little sample task, and this is one that we're going to come back to many times during this presentation. In this particular example, each trial will consist of a target turning on. It's going to happen at the beginning. Then the subject is supposed to reach to the target. And once they do, the target moves to a new location. And then once the subject reaches the new target, the target will turn off and the trial is over. You'll notice that this is what I mean by a generic paradigm. We didn't specify any parameter values. We didn't say where the target was. We didn't say what color it was. We didn't say how many trials. Those are detailed parameters that can be used to help fill out what is actually going to happen when a task is actually run. So how do I go and use these? Back in the Dexterity user interface, in the task tree, you will remember that there are two levels. And the first level is actually the task programs that are available. And then the second level is the task protocol. So each task program will have one or more task protocols associated with it. And when you select task protocol and you click go, what's going to happen is the Dexterity computer will download both of these over to the robot computer, and then the task will run. So how do we create a task program? Well, I need a development computer. All right, so this could be your laptop, could be another computer in the office. It could also be the Dexterity computer. What's important is that this development machine is going to have various tools on it. So MATLAB, Simulink, and C compiler and such. And that allows you then to program and build your task. What's important though is that this is what you need for developing, all right? MATLAB doesn't actually run during an experiment. It is only the development environment. Let me start with a brief introduction to Simulink, which is one of the key tools that we use. It's a high-level graphical programming language. An example can be seen here. Being a high-level graphical environment means that it's easy to visualize data flow, and this is one of the nice features about it. I can see where the data is going to flow, how it's going to go from one block to another block before it gets to another block. And so it gives me a very high-level understanding of what's going to happen. It has a hierarchical structure, so I can embed all sorts of Simulink code within a Simulink block, so I can hide the details. And this is, of course, important because, again, it means that if I want to have just a high-level view, I can maintain that, and I can bury the details that maybe I worked out at a different point in time underneath. I can embed MATLAB code. People who are used to coding in C, Java, or Python are used to actual code, and sometimes can be a little bit scared by the graphical nature of Simulink. And so it's important to recognize, well, you can embed MATLAB code in here because sometimes coding is far more efficient and far easier than using a graphical language. And so you really can get the best of both worlds. And the last point I want to mention is this little middle block, which is actually a stateflow chart. Stateflow is a toolbox within Simulink, and it has huge value because it provides a very nice environment for collaboration. And what I mean by that is that if you are working either with someone or for someone and you want to try to communicate what your code is doing, looking at MATLAB code and Simulink code is sometimes very confusing. But the stateflow chart, which I'll get to a bit later, really sort of is the meat of what is actually, what's the behavior of my system going to be. And this provides a nice interface to allow you to share that and for other people to easily understand. All right, so what's going to happen when my Simulink code actually runs on the Kinarm? Well, the first thing that's important is that everything you see is going to execute once per clock cycle. Our robot computer runs at 4 kilohertz, so that means every block you see here, all right, all 8 of them are going to execute every 0.25 milliseconds. And they execute in a specific order. They're going to start at sources. How do I know that these two are sources? Well, I can see that there's no data going into them, only data going out. So this is where things start. Data then flows along these arrows, flows along this path, it goes to the next block, to the next block, to the next block, and then it ends at a sink. How do I know it's a sink? Well, there's no data streams coming out of it. Now, for those of you who are paying attention closely, you might notice that it appears that there's something breaking this rule I just said, because it looks like there's a little infinite loop there. But what's actually happening is inside this block, there are many other little Simulink blocks, and there are actually sources and sinks inside. And so it really is a truth that execution always starts at sources and always ends at sinks. Well, where do I find these blocks? All right, I've opened up Simulink. I want to start doing stuff. Well, I have to go to something called the Simulink library browser. So within Simulink, if you click on this icon, it'll open up this browser. And there are a number of libraries that'll be in there. So Simulink and Simulink Real-Time are a couple libraries that are contain a lot of blocks that you'll end up using. But in addition, you will have installed our task development kit, which will make this dexterity library show up. And these are all sorts of blocks that we have provided that are required to run a Kinarm. So there's a few that are required for every task, and then there's lots that are optional. I'll just briefly describe these ones that are required. First is the GUI control block. This really provides the main interface between the dexterity computer and the robot computer. So the operator is over in the dexterity computer and they click start or pause or stop the task. Well, that information has to somehow be communicated over to your code, and that's all handled magically in the GUI control block. GUI control block is also managing where you are in the block table and trial structure, so which trial is being executed at what point in time. I'll jump over to the data logging block. This is something that basically collects all the data, make sure that everything is all synchronized together, and pushes it back over to the dexterity computer. So even though all the data is acquired on the robot computer so that we make sure we've got robust synchronous data, it's actually saved so that the operator has access to it back on the dexterity computer. And so this handles that kind of functionality. We then have the parameter table definition block. This block is one that allows the person programming the task to decide what is going to show up in the task protocol. So when an operator is making a new task protocol, they're editing one, they will have various parameters that they can change. And this is where those parameters are defined. It defines not only sort of the names, but also descriptions for them. And it also defines how they can be used by the code in here. And the last is this trial control block in the middle. This is a state flow chart, which really controls the behavioral state of the Kinarm during each trial. And I'll explain more detail about that one later. I'm just going to show you a couple other common Kinarm blocks. Many tasks depend on subject behavior. Has the subject reached a target or not? And so Kinarm hand and target block provides you information about whether the subject has reached a target. Often you want to present visual stimuli, so you'll have these kinds of blocks. And you may want to present loads. And so you'll have various loading blocks. The visual stimuli and loading blocks are covered in a later presentation, so I won't talk any more about those here. I'm now going to switch over to, again, a very brief introduction to Stateflow. Stateflow is a toolbox within Simulink, and it is where you can define something called an event-driven system or a finite state machine. And although it's technically not a flow chart, it kind of sort of feels like one. And the main two elements are states and transitions. And the idea is that, sort of like a flow chart, you're typically in one state at a time, and then there are paths or transitions that tell you how you get to the next state. And transitions can have conditions on them that say whether it's valid to take that path or not. And so again, although it's technically not a flow chart, it's kind of similar to one. But what's nice is it really formalizes the design of an experiment's flow. So people always, can easily describe and talk about their experiment, but sometimes if you have lots of branching, it can get complicated to explain. And Stateflow, it formalizes it, which forces you to actually think about whether you've defined all the states that you want to or not. And it allows someone else to actually look and see if they've defined them the way that they understand as well. Stateflow execution, so even though it works within Simulink, it's a little bit different than Simulink. And this terminology comes from MathWorks. So when a stateflow chart executes, what that actually means is the transitions are going to be examined to see, are they valid or not? So it doesn't mean you're going to execute or you're not going to follow a transition. You're simply going to look to see if it's valid. And if it is valid, then the transition will occur. So it may result in a change in state, but it may not. So in this example, the one I showed earlier, if you imagine the system was in state 1, when the stateflow chart executes, it's going to look at this transition. It's going to see there's a condition, and it's going to evaluate that transition, right? Is the hand in the target? Okay, well, if it is, then the transition's true, and we'll move down to state 2. If it's not true, well, then we don't execute the transition, and we simply stay in state 1. So when do state flow charts execute? Well, anytime that an input state flow event occurs. Because you, the programmer, get to define the state flow events, that means that during a single Simulink frame, it's possible that more than one state flow execution can happen during a single time frame. So in other words, you can have multiple state transitions during a single time frame. You could also have the opposite occur, where there are no events, which means there'll be no transitions occurring. We, to help assist with people, provide a 1 kilohertz clock input state flow event to ensure that you can force your state flow chart to execute at least once per millisecond. I'm going to recap some of those differences I just described between Stateflow and Simulink because it is a little bit confusing. The first is that Simulink code is running continuously at 4 kilohertz. So every block is going to execute once every 0.25 milliseconds. Doesn't matter what the inputs are or not, they're all going to execute. In contrast, a stateflow chart is event-driven, so it doesn't run at a fixed rate. Whether it happens to execute or not depends on what is actually happening in the stateflow event inputs. Another difference is that typically all parts of the Simulink code are active. So all the blocks that you see are going to execute every single time frame. Whereas in contrast, in Stateflow, typically you only have one state active. And so therefore only one state is typically executed at most per Stateflow event. That provides some background on some of the tools that we use. I now want to start talking a little bit more about, well, how do we actually build the task? What do we do? And of course, you have to start with an idea. I like to then take a pen and paper and actually write a flowchart. What is actually going to happen during a trial? And this is the part where you want to make sure you're collaborating either with your advisor or with someone else that you're working with to say, all right, let's think about all the things we want to happen. All right, if this happens, then what? If this happens here, then what? Because if you've got that part laid out correctly, that really will simplify the following steps and you won't have to redo them all. Because the next step is to convert that flowchart into a state flowchart. You then, add the necessary blocks to make sure that information is going into and out of the state flowchart. Then there is the most time-consuming part, which is your testing and debugging. So let's walk through an example, and this is that example I showed earlier. So during each trial, the target's going to turn on. Then once the subject reaches the target moves to a new location. And once the subject reaches the new location, the target turns off and the trial is over. This is what the Simulink model might look like for that task. We have to have the blocks that we always need. We have a GUI control block, we have a data logging block, and we have the parameter type definition block, and we have our state flow chart in the middle. Various of the so-called optional blocks, well, I'm going to need a Kinarm hand and target because this block tells me if the subject's reached the target or not. So I know I'm going to need that. I know I'm going to want to show targets, so I need some blocks that will show the visual stimuli. And although I didn't say so, in this task, I'm going to assume I want to show hand feedback to the subject so they have some idea where their hand actually is. So let's take this task, and this is the exact same description I showed earlier, and start writing out what it might look like sort of as a flow chart or on pen and paper. So at the beginning, a target's going to turn on. This is what's going to happen during a trial, all right? And the system, after it's turned on the target, it's going to just wait. The system waits in that state until the subject's hand is in the target. All right, that's the condition that we care about. Otherwise, the system just waits and waits and waits. Once the subject's hand is in the target, okay, well, we can change the target location. And then again, we wait. The system waits in the state. It doesn't do anything different, doesn't change anything until the hand is in that new target. And once that's true, great, then we can say that's the end of the trial. And we can, turn off the target. So that's sort of the first basics. There are, of course, going to be some extra details we need to add in. And the first is, well, if I want more than one trial, I need a way to get back to the beginning. And I also need a way to tell Dexterity that the trial's over. It doesn't know when a trial is over unless you tell it, because there's nothing, magical about it knowing that you've decided that there's only going to be, 2 movements in this particular trial. So you have to explicitly state that the trial is over so that the system knows to, okay, let me go get the details about the next trial so we can then go and start the next trial. All right, well, that's great. But now I've got a loop. Where do I start at the very beginning? So I am going to have some place to sort of initialize right at the very beginning of the task so I know where to start for the first trial. There's a second thing that I've added. Notice down here that there's now 2 transitions, all right? So when the state flowchart executes, if there are multiple transitions, it'll look at both of them. And if either of them are true, it'll follow them. Now it'll follow them in the order that's been numbered. And you'll see what I've done is I've added a transition that says wait for a specified period of time. This is what I call a timeout. It's really useful to have timeouts because it's important to recognize the system will do what you program it to do. So if I don't have this timeout, and you'll notice I don't have a timeout up here. So let's suppose that the first target turns on. Well, what happens if the subject doesn't reach that first target? Well, the system's going to stay here forever. It doesn't know that you might want to exit after a certain period of time. It doesn't know that you might want to say, well, after 20 seconds, we should just time. You have to program that in. So if you want a way out of a state, you have to explicitly add it in there. If you don't add it, then the system won't follow that desired behavior. So you have to program everything in that you want. Once I've got this, then, and this is all again just sort of descriptions here, but then I get to add all the code. And this is what the Stateflow code would look like for this particular example. And of course, there's a lot that's just been added there. So let me walk through little bits of it, and I'm going to take a step back and provide a few more details about this programming environment. Stateflow has variables. Right? This is the same as pretty much every other programming language. And like most other programming languages, a couple of the data variable types you have are constants and local variables. So a constant is just something that you define once. And so rather than the number 2, putting it everywhere, you define it as a constant. And that's just a much more descriptive, easier to read way of programming. Local variables are variables that are local just to the Stateflow chart. So that means I can use them somewhere else in the Stateflow chart. So you can see that time interval is used here and used here, and that's the same variable, but it's not visible outside of the Stateflow chart. Well, okay, but how do I get data into and out of the Stateflow chart? Because of course, it needs to interact with the rest of the Simulink model. Well, that is through 2 other data variable types, which are called Stateflow inputs and Stateflow outputs. So if I've defined something to be an input, a Stateflow input, then it will show up in my Stateflow chart, and I'll be able to connect a signal into it from another Simulink block. So this is how I can send data into my Stateflow chart. And that means, well, I can read from it. So I can, set some variable equal to whatever is in that. Outputs, of course, are the analogous thing on the other side, where if I define something as an output, it will show up on the output side of my Stateflow chart, which means I can then use it to drive other parts of my Simulink. But it means that I need to assign values to it, just like I would any other variable. So that's how inputs and outputs work. How do I define something to be a local or input or output? It's through the Model Explorer. Within Simulink, if I find this icon, it's called the Model Explorer, and I click on it, a window will open up like this. Basic task is the name of the Simulink model that I'm working on right now. Trial control is the Stateflow chart that I was working on. So if I've highlighted that, I can then click on this icon here, which will create a new data variable. And I can then I can give it a name, and I can define its scope to be an input, an output, or a local. So those are your sort of normal variables. But Stateflow has something else called Stateflow events, which are different, something that's not found in most other programming languages. And these are useful because they can be used to trigger transitions. If I have a Stateflow event on a transition, so this is now my condition, well, what that means is that if something else calls that Stateflow event, then this transition will be true. And this is how I do that. If I execute, if I put it as a command line, then that Stateflow event will effectively execute, and it'll be broadcast to wherever else it's used and said, hey, the Stateflow event has just occurred. And I can send these in and out of my Stateflow chart. All right. So if I define something as a Stateflow input, then that means some other code somewhere else can send a Stateflow event into my Stateflow chart, which would cause this transition to be true. And likewise, if I've defined something as an output stateflow event, then it will appear on the output side of my stateflow chart, and I can use it to drive some other code somewhere else. How do I define these? Same way as I define the data variables. I go to the Model Explorer, and I click on this icon here, and it's going to open up the Model Explorer again. But this time, I'm going to click on the lightning bolt symbol. And that would create a new stateflow event down here where I can choose and select its input and output. A useful feature of stateflow that works with stateflow events are something that are called temporal logic operators. And you can look in stateflow help for various examples of these. The one that you will see most often in many of our sample codes is the after operator. And it's you'll notice that the syntax is highlighted in blue when you go into your Simulink code. And it is an operator that will return true after this many of this stateflow event have occurred. So millisecond is another sort of special built-in stateflow timer, and not surprisingly, it occurs once per millisecond. So what this means in this example is, since I have assigned tick count a value of 1500, that means that after 1500 of these events, so after 1500 milliseconds, this transition is considered true. So this is how I can create a timeout in my code. I now want to talk about the parameter table definition block. As mentioned earlier, each task program needs this block because this is how you as the programmer are going to specify and define what the operator sees when they go to edit a task protocol. So if I click on this block, I will see a dialog like this. And I can click on the plus and X to sort of create new ones or delete existing ones. I can change the order up and down with these up and down buttons. And then for each one of these, I need to complete the row. And most of it is going to define what the operator will see when they go to edit task protocol. So there'll be a name that they'll see, and there'll be a description, which should of course be helpful in some manner for them. You also, though, can define a constant, which is going to be equal to the column number, or basically this is the element in the TP table, that can be used in Simulink and Stateflow. And that can be very handy when you're programming, because when you're programming, you're going to want to be able to access elements in the task protocol. So what do I mean? And let's try to put this all together. And there's a lot going on in this slide. So if we focus first off, the parameter table definition block, this is where I'm in Simulink. I've double-clicked on that block and open up that dialog, and I start entering in labels for these different columns. Well, what does that do? It means that in dexterity, when the operator goes to edit a task protocol, that's where the labels come from. They come from whatever you type in here. So then the operator is going to fill in numbers, and at some point, these numbers have to have an effect. Well, where do they have an effect? Well, the GUI control block outputs something called the trial protocol. All right, and there's a block table that says, okay, which trial protocol am I going to use at which point in time? And so if at some point in time it's time for trial protocol 2 to be executed, then that means this row in the TP table is what's going to be put out on this data stream here. So there'll be a vector with 4 elements, 2, 5,000, 200, and 500, that's going to be passed over here. So in my stateflow code, this is where I then can extract the numbers from the trial protocol. And so, of course, what I'm going to want to do, though, is, well, trial protocol is a vector. Which element do I want? Well, that's where these columns, these constant names come from, because they are related to the columns. So start target column is a constant, so it has a value of 1. So that means that here I want to look at the first element in the trial protocol, which would be this 2 up here. So that's how all of these different elements work together. There is a lot here. I would recommend, if you haven't already gone and played with the task protocols, make sure you get experience with that before you start trying to program tasks and play with these. And then you can start playing with these one at a time and seeing what happens and understanding how they relate to each other. I'm going to mention a couple programming tips. The first is something that we call event codes, all right? And these are things that can be really helpful when you're troubleshooting, debugging, and verifying a task. And they're also very useful for post-experiment analysis. What you can do is when you log an event code, that gets saved in your data file. So typically when I create a state flow chart, every single state flow chart, every single state within the state flow chart, I am going to assign the event code to a unique value. So that way I have a record of when that state was entered during my task. It's important, just by the way, to note these are different from state flow events. They are not a state flow construct. They're something that you define. And so again, this is useful for a whole number of reasons, very simple to add in, and very useful for debugging, verification, and data analysis. Another useful tip is to take advantage of something called Simulink Real-Time Scope. So this is a block that is part of the Simulink Real-Time library, so we didn't provide it. And if you click on it, it'll give you a few different options. So where it can display information, it's numerical or graphical, so it can look and act just like a real oscilloscope, but it shows up on the screen of your robot computer. And so this allows you to be looking at various data and signals in real time while your task is performing. So again, this is very useful when you're trying to debug or verify your task and ensure that it's actually behaving the way you want it to. Okay, so let's imagine you've gotten, you've programmed your task, you've spent your time in Simulink and Stateflow. Well, how do you deploy it? Well, Simulink and Stateflow and MATLAB are just the development environment. You actually have to build the task. You have to create compiled code. And so this is done with basically you just type Control B and then you sit and wait. And then Simulink will compile the task. This often takes a few minutes. It can create many intermediate files. But it goes through a couple different steps. And if it encounters problems for whatever reason, it'll stop and warn you and say, you haven't, defined this, or I don't understand that. So for example, you can get, it might come up and show there's some compiler errors, and this window will show up. Generally speaking, look at what the error message is. Look at the first one, all right? Often a given error will generate a bunch of subsequent errors that all get magically fixed if you fix the first error. So focus on the first one. In this example, okay, there was an undeclared identifier. That means I tried to use a variable that I hadn't defined. So sometimes the Simulink provides really helpful error messages. Sometimes they're a little bit cryptic and you might need to go Google it to find out what it means. But in generally, you can't go any further until Simulink has decided that all the appropriate errors and such have been fixed. And so if that happens, then great, you'll get a, okay, compile successful. All right. Well, I still need to do a few more things in the deployment because I have to take it and make sure that this code is in the right place so that Dexterity knows it exists. So what matters is the MLD ATX file that was just created. So whatever your task was named, whatever the source code was named, that'll be the name of your MLD ATX code. So you need to take that file and you need to go to Dexterity. Every Dexterity version has its own folder. Every task program has its own subfolder. And so it's important, there is only one MLD ATX per subfolder. If you have multiples, Dexterity will only look at and show you the first one. It won't even indicate to you that there's a second one or not. So there's a few other files that matter in there, and I'm just going to show how they map. The MLD ATX file is the name of the task program. That's what the operator is going to see when they open up Dexterity and they go to try to run a task. As a side caution note, don't rename the MLD ATX file. Simulink Real-Time doesn't recognize it if you've renamed it, unfortunately, so you have to keep it the same. Other files that are going to be present are DTP files. So these are the Dexterity Task Protocol. And you notice you can have one or more per task folder. Each one of those will show up as a task protocol in the tree in the Dexterity user interface. There are a couple of optional files. So if your task requires graphics to show, and that's a part of later presentation on visual stimuli, but this is where you would put that. And likewise, if you wanted to provide an instructional video so that when you started your task, you could just show a video to your subject so they could, watch what is actually going to happen, this is where you would put it. Again, both of those are optional. And the last one that's optional is the source code for the task. So this isn't required by Dexterity, but I tend to try to keep my source code and my compiled code together, because that way I can always find it. If I need to make a change to it, I can't go backwards from my MLD ATX code to my Simulink code. So I need to keep them together. And the last thing I just want to point out is, where do you go from here, right? Because this is the end of the task programming talk. Kinarm Academy is on our website, and this is where you can go and learn and find all sorts of not only other instructional videos on how to use the Kinarm, but there's also a lot of information on exercises and solutions to exercises so that you can take what you've learned here and practice and see if you've understood what's happening. Thank you for your time.